Okay, so as I said, we are now looking at functionals of the form j of gamma, which is equal to the integral from 0 to 1 of f of x dx dt, y dy dt. Sometimes you'll have a t in there, but in the isoperimetric problem which you'll have, we won't have a t, and this will be integrated with respect to t. And so this is some functional of a parametric curve, which again, you have some gamma, which you can consider as a function of time, as being x of t and y of t. So these are just some parametric coordinates. And these you can think of as just as tracing out some curve. And so we'll enforce that gamma 0 equals gamma 1. And we can fix those coordinates, say as being x0, y0. So all that's saying is that this condition says that it's a closed curve. This condition is that you fix the starting point to be x0, y0. So that would be x of 0 is equal to x of 1 is equal to x0. And y of 0 is equal to y1 is equal to y0. So now we're looking for an extremal value of this, which, to remind you again, we can sort of think about a minimum. So we can say that like gamma bar or something is minimum of j if for all small h j of gamma plus h is greater than or equal to j of gamma. So what does gamma plus h mean? Intuitively it makes sense. It should just be like a small sort of change of this parametric curve. So it's something that's like not too extreme. Like if we had something like this, then that's like a very extreme difference from our original parametric curve. But this first one may be gamma, and the second one may be gamma plus h. So that means that h is really also another parametric curve of two coordinates. So we can write, let me erase this picture a little bit and redraw that. So this is our curve gamma. It's our starting point, and then we can have like gamma plus h. So h of t is also some parametric curve, which will be h1 of t, h2 of t. And then what we mean by gamma plus h is that we add the coordinates. So x of t plus h1 of t, and y of t as the second coordinate plus h2 t. So if we add a sufficiently small value of h, which again, don't worry about sufficiently small, because by doing this sort of thing, we'll get something that must be true for all parametric curves h. But anyway, so for small enough h, where we just fix the starting point for convenience, we have that j of gamma plus h is greater than or equal to j of gamma. So the nice thing about introducing the language of the calculus variations in terms of like the first variation instead of jumping right into a derivation of the Euler-Lagrange equation is that it allows us to generalize to cases like this much easier. So we still have the same statement that if this is true, then delta j of h, whatever that may be, is equal to 0 for all h. So what is delta j of h again? Again, we can sort of write j of gamma plus h is equal to j of gamma plus delta j of h. Again, there's an implied gamma in here, but we're really focusing on this little augmentation, which we call h, plus, I think earlier I wrote it as like magnitude of h times some epsilon of h, but I think it's just better to write it as o, small o of h. And this means that this is just some function, you can think of this as some function f of h, such that f of h divided by magnitude of h goes to 0. So this is just called small o notation, and yeah. So f of h over magnitude of h goes to 0 as the magnitude of h goes to 0. So now we have this sort of expression and we have that delta j of h is equal to 0. We can pretty explicitly get this variation by looking at this and using the same sort of expansion trick that we had in the one variable case. So we have that j of gamma plus h is equal to integral from 0 to 1 of f of, so remember how the x-coordinate is now replaced by x plus h1 because our h is h1 of t and h2 of t. So this will be f of x plus h1, and then here we're taking the derivative with respect to t of x plus h1, but because derivative is linear we can just split it up. So this will be, instead of writing dx dt, I'll just write x prime plus h1 prime, and then we have y, but y is just replaced by y plus h2. This will be y plus h2, comma y prime plus h2 prime, and then t is left unchanged. Again, we don't really care about t too much. So this is gamma, j of gamma plus h, and what we can do is we can subtract of j of gamma, and instead of writing it out as two integrals, I'll just subtract it off inside the function. So this will be minus f of x, x prime, y, y prime, t, all of that dt. So now again we're gonna use a sort of expansion of all of this using the Taylor series first order approximation thing. So you can sort of think of each of these as being independent variables. Like you can call this x, w, y, v, and t, and then you can sort of change each one. But essentially what you end up with is the integral from 0 to 1 of h1 partial f partial x plus h1 prime partial f partial x prime plus h2 partial f partial y plus h2 prime partial f partial y prime. Yeah, that's it. And all of that dt. So what is this again? So you can think of this as being, you can sort of ignore the t, because again, we usually won't be working with functions that depend explicitly on time. So you can just sort of ignore that. And you can think of this as being some function that goes from four-dimensional space to one-dimensional space. So it's like a function with four inputs. So this is saying, let's call these coordinates x, w, y, and v. So this first one is saying you increment in the x direction by h1. So the difference between this and your original function is just h1 times the derivative, times the amount that you change in f by a small change in x. This one is saying that you're moving by quantity h1 prime in the direction of w. So the amount that your function changes is, like, again, your slope times your width, and your slope is partial f partial x prime, which is how much your function changes in the x prime direction, which is just the w direction for each small change in w, and h1 prime is your small change in w or your small change in x prime, and so on for the rest of them. And so again, this is just the same thing as like sort of f of x plus t minus f of x approximately equal to t times f prime of x. So like if x is small, if t is small. So this is like just sort of, if you have your function here and this is your point, then you have some slope and your vertical change, which is represented by this quantity. So this will be like x plus t comma f of x plus t. So this vertical quantity, which is this, is roughly equal to your horizontal quantity times your slope, and your slope is given by this, and your horizontal displacement is given by t. So it's just the same thing here, applied multiple times. Okay, so now I won't do out all of the calculation, but you can do the same sort of thing we did last time. Because we have h1 prime and h2 prime, we sort of want to get rid of that derivative. So we can do integration by parts again, this time with respect to t. And we'll get that this becomes integral from 0 to 1 of h1 times partial f partial x minus d dt partial f partial x prime plus h2 partial f partial y minus d dt partial f partial y prime dt. So you can think about why the sort of boundary terms go to 0, and that's again because we want to fix the initial point. So we'll have that h1 of 0 and h2 of 0 are both, and h1 of 0, h2 of 0, h1 of 1, and h2 of 1, because t is on the interval 0 to 1. All of those values are 0 because the initial point is the same. And so we have that the boundary terms cancel, and then on the inside you have this sort of a thing where you take the derivative with respect to t of this guy and you just subtract that off. Okay, so this must be true, this must be equal to 0. Put an equality sign in. This is approximately equal to. This is equal to, this one's approximately equal to. But then this one is going to be equal to your first variation of h. And so this first variation must be equal to 0 for all values of h. But h is some coordinate function of t, h1 of t and h2 of t. So we can sort of change h1 of t and h2 of t independently. So what I mean by that is you can fix the sort of y coordinate and just change what the x coordinate becomes. So this is like, I tried to keep the y, okay, so this one is like keeping the x coordinate the same, but decreasing or increasing the y coordinate with time. So this will mean that h1 of t is equal to 0, but then this one is not equal to 0. So in that case, what you have is that because h1 is 0, and again, this is like a particular value of h, but this must be true for this particular, or not a particular value, it's like a particular classes of functions of h, or parametric curves h, where the first one is 0 and the second one is non-zero. So let's assume that h1 is equal to 0. Then since this is true for all h, then this must be true for all h where h1 is 0 and h2 is non-zero. But since h1 is 0, that means that this first guy is going to be 0. So that'll mean that this is the integral from 0 to 1 of h2 times partial f partial y minus d dt partial f partial y prime dt. And this must be true, this is equal to 0 for all h2. And h2 is now just a function of t. And because this must be true, we must have that this guy is equal to 0. So from that, we deduce that partial f partial y minus d dt partial f partial y prime is equal to 0. And by similar logic, you can sort of change the x coordinate while keeping the y coordinate fixed. So that'll mean that h2 of t is equal to 0 and h1 of t is non-zero, which will mean that this term goes to 0. So you can sort of ignore this, and you have a functional with respect to one variable. And because this integral must be 0 for all h, it must also be 0 for all h where h2 is 0 but h1 is non-zero, which will imply that this inside little bit is also equal to 0. So what that means is that we have partial f partial x minus d dt partial f partial x prime is equal to 0. Okay, so what we have is we start off with a functional that looked like f of x, x prime, y, y prime, and t. And we're integrating that from on the interval 0 to 1 with respect to t. And we said that if we want an optimal or an extremal value of this functional, which is some gamma bar for which j of gamma plus h is greater than or equal to j of gamma, or should I put gamma bar is there. If this is true for all small h, then this must be true for all h, which means that this integral must be 0 for all values of h, where again h is some parametric sort of augmentation curve. which means that this must be 0 for all h. And then we sort of said if this is true for all h, then you set h1 to 0 and h2 to 0, then you can get these two sets of equations. So these are equations which will give you information about gamma, which again we found by setting this equal to 0 for all values of h, which is the same sort of thing we did in one variable. But anyways, these are your sets of Euler-Lagrange equations for a parametric curve of this form, such that you get an extremal value. And this is what we'll use to help us solve the isoperimetric problem. In the next video, I think I'll probably go over the Euler-Lagrange, not the Lagrange multipliers, generalization, where we look at two different functionals, we keep one of them fixed and then change the other one, and then show that that implies that you have that sort of Lagrange multiplier type phenomenon going on.